Good evening. So, do you have any questions from the previous class? Any questions? So, today we are going to discuss the residue theorem. So, this is one way of finding the integral. Again, the same integral what we have found with the help of Cauchy's theorem or Cauchy's extension theorem or Cauchy's integral formula. The same purpose is even done with the residue theorem also, but in a different way. So, first of all, we need to understand what is this residue. So, that is the coefficient of z minus a whole power minus 1 in the expansion of Lorentz series is termed as residue. So, this is termed as residue. Usually, this is represented with C minus 1, the coefficient minus 1. So, which is nothing but the coefficient of z minus a whole power minus 1. This residue, what residue theorem states is, if a function is analytic in a region R except at a finite number of singular points then the integral over the contour C or over the region R f of z dz is equal to 2 pi I times of residue at all the singular points, sum of the residues. Singular points. This is what residue theorem states. Suppose if there is a region identified by this R, in this region, except at certain singular points. So, this is the region of integration, and in this region, the function is analytic at every point except at point A1, A2, A3, A4 and A5. So, at all these points, the function is not analytic. In such cases, the integral value, integral f of z dz over the region R is equal to 2 pi I times of residue at f of A1 plus residue at f of A2 plus residue at f of A3 plus residue at f of A4 and residue at f of A5. So, this is what is the residue theorem states. Got it? Any questions on this? Any questions on this? So, you can note down this residue theorem. Done? So this is about the residue theorem. So in this actually frequently we are using one term called singular point. What is this singular point and what are the different types of these singular points? There are different types of singular points, right? So singular point is nothing but a point where the function is ceases to have a derivative. So that's the point actually where we call as the function is not analytic or it is a singular point. Now there is something called zeros and poles. So suppose if there is a complex function f of z, let us say this is z minus z1 into z minus z2 into z minus z3 divided by z minus p1 into z minus p2 into z minus p3 into z minus p4. Suppose if this is a complex function, now in this case, if so the values of z makes f of z is equal to 0 are called zeros of the function. Now in this case, what are the zeros of the function? What are the zeros of the function? No, it's not correct, Kavya. So Hitesh gave correct answer. So zeros of the function are z1, z2 and z3. So these are the zeros of the function. Right? Now, what are the poles of the function? So what are the different poles of the function? So obviously this will be P1, P2, P3 and P4. These are the poles of the function which makes the denominator 0. So the values of z which makes the denominator 0 are called poles of the function. Now, in this function, if you notice, suppose if there are powers, that is z minus p2 whole power 3, like that if it is there, then we say that this pole is of order 3. Now, the relation between a Lorentz series and this order is nothing but if we expand with Lorentz expansion, Lorentz series, suppose the negative powers of z minus a whole power minus n vanishes after n, first you note down this, I'll erase it and write it. Note down these things, zeros and poles, then we will go to the higher order poles. Let me know once you note it down. Done? Now in this, the Laurent expansion, suppose if the negative powers, I'll just write it here. We expand the function f of z as Laurent series, suppose if negative powers of z minus a vanishes after n, then we say the pole is of order n. The pole is of order n. Suppose if n is equal to 1, then the pole is said to be a simple pole. The pole is said to be a simple pole. So pole of order n or pole is said to be of simple pole. So these are two different kinds. Suppose this z minus p2 whole cube is there, then p2 is a pole of order 3. And all other poles are simple poles. Simple poles. Got it? Suppose if the series doesn't vanish, the Laurent series, negative powers goes to infinite, then the singular point is called as essential singularity. Essential singularity. Got it? Noted down? These are the different kinds of the singular points. So pole of order n, simple pole and essential singularity. Any questions on this? Any questions? Okay. Now, based on this understanding, we will solve some problems. This is on residue theorem. So there is one more thing, the calculation of residue. Now the calculation of the residue, suppose if f of z is there, and for this function at z is equal to a, residue at z is equal to a is equal to limit z tends to a, z minus a into f of z. This is the way we calculate the residue. Got it? Limit z tends to a, z minus a into f of z. So if this function contains a pole of simple pole, z is equal to a, that is z minus a, if you multiply it, it will cancel with the denominator, and remaining thing get substituted z is equal to a, you are going to get the residue at f of a. This is residue at f of a. Suppose even after putting z minus a, usually this is the way, f of z is equal to z minus z1 into z minus z2 into z minus a into z minus b into z minus c. If this is the function, now there are three different poles. Now all the three poles, you can find out the residue value by just substituting z is equal to a after multiplying with z minus a. So I am going to explain all the cases. This is one case, how you can find out the residue. So this is case 1. In the case 2, even after multiplying with z minus a, if still the function is, after substituting the limits, if it is coming out to be 0 by 0 format, then you can find the limit value z tends to a after doing the derivative with respect to z in the numerator. So in f of z, so this I call as phi of z divided by psi of z. So this I have written as phi of z divided by psi of z, so that I can apply the L'Hospital rule. Now this psi of z, if you do the derivative of it, the numerator will be limit z tends to a, and this is UV formula you can apply, z minus a into phi dash of z plus phi of z into z minus a derivative is 1, in the denominator psi dash of z. Now after substituting the limit value z tending to a, this will come out to be, this term will become 0, and this will be phi of a divided by psi dash of a. This is the residue at f of a. So this is case 2. The case 1, you simply substituted the limit value, you got the finite value, which is we call as the residue. But in case 2, even after substituting the limit value, if it is coming out to be 0 by 0 format, you will apply the different format. Numerator you will take it as it is, denominator you will take the derivative and substitute it. I didn't get your question, Samrin. Residue is what? Zeros and poles are there? I didn't get that question. Can you repeat? No. So your question is, are you getting confused with what is residue and what is pole? At every pole, there will be certain value of residue. So pole is different. Pole is, is the value of z where it makes the denominator 0. That's what we call as pole. But residue is nothing but the value that needs to be considered in the integral part, because the Cauchy's theorem will not be able to find out the integral value because there is certain singularity there, and that singularity is defined by this pole. Got it or not? Right? So pole is different, residue is different. Residue you can find it out if there is a pole at that point. If there is a pole presence, then there will be certain residue value. That residue value you will be identifying to calculate the integral value. This is one way of finding the integral value. Now this pole has very high level of importance in case of electrical engineering and even in the control system engineering for mechanical or civil or electrical engineering persons. So this pole, if there is a pole at this point, so this is, let us say, it's a transfer function of a system. Transfer function of a system means which gives the relation between output and input. So that is usually a complex function. That complex function, so if there is a pole presence, then this function will be infinite automatically. So if it is infinite, definitely the system will not function as expected in control system. So usually the system is termed as a control system. So you will not be able to control that system at the position of z is equal to a. So this z is equal to a is dependent on the physical parameters of the system. Got it? So if there is a 0, then the output is coming out to be 0 itself. So if it is 0, then actually we can make the system stable. But if z is equal to a, where the pole is there, then the system value, so the gain is coming out to be infinite. That means it will go on to the resonance and then finally the system will fail. Got it or not? So such kind of analysis or the physical analysis where we are going to use this complex function. But from our mathematics point of view, you just need to understand if there is a pole presence, then at that point there will be a certain residue value that will be left over, which you can make use to find out the integral value. Clear now? So this is one way of finding the residue. So in case 1, this is a simple pole. In case 2, at this value, it is not coming out to be a finite value. Still you have to apply L'Hospital rule and find out the residue value. This way you can find out the numerator, you can substitute the a value as it is, but the denominator you need to take the derivative and substitute it. Then you will be able to find out the residue value. In case 3, residue at a pole of order n. So if there is an order n for that pole, then the residue value you can find out limit z tends to a. So the pole is of order n. That means let us say z minus a whole power n is there. That is the pole of order n. Then you have to multiply that function with the same value z minus a whole power n into f of z. Then after multiplying this, right? So here, if it is a simple pole, you are straight away substituting it. But if it is a pole of order n, what you need to do is you need to multiply this value with 1 by n minus 1 factorial and do the derivative n minus 1 times with respect to z. Just write it here. Limit z tends to a and 1 by n minus 1 factorial d by dz power n minus 1 n minus 1. So you need to multiply with z minus a whole power n and then do the derivative n minus 1 times, and then 1 by n minus 1 factorial is nothing but the residue value at f of a. So this is a complex pole of order n. So this makes the importance to it. These are the 3 different kinds of cases how you can find out the residue. Why we are finding out this residue? Because you wanted to find out the integral value. Got it? Understood or not? Any questions on this? Okay, so with this understanding, I hope you noted down. No derivations are required. These are just formulas you can make use of. So residue is nothing but the coefficient of z. So z minus a whole power minus 1. Now, if it is a simple pole, straight away z minus a whole power minus 1 into z minus a. Straight away it will make a constant value. Correct or not? In this expansion of Lorentz series for f of z, there will be a factor of c minus 1 into z minus a whole power minus 1. Now, if you multiply with z minus a, then these two will cancel out, the constant will be left over as limit z tending to a. So that's where, as it is being a simple pole, there are no other powers of z minus a, negative powers other than z minus a whole power minus 1, because that's what we mean the simple pole. There are no higher powers of order more than minus 1. So that is a simple pole. If you multiply with z minus a, automatically you are going to get the value of c minus 1, which we call as the residue by definition. And so these are the different ways of finding c minus 1 for different cases of poles. Nothing more than that. Got it, Kirandeep? So same is the case. If you take the other case, suppose even after multiplication of z minus a, if it is coming out to be 0, then you are doing that way. Now if it is a pole of order n, then z minus a whole power n, if you multiply it, then there is a possibility of numerators coming out to be z minus a factors. Then if you substitute z is equal to a, so all other factors are going to be 0, then you will be able to find out the c minus 1 value with the help of this after taking the derivative of it. Clear? Got it? So by multiplying this factor and doing n minus 1 times derivatives, it will vanish out all the values of order z minus a whole power minus 1 more than that. Yeah, you can still find the, so that is expected. So you can make use of the Lorentz series and find out the c minus 1 value, and then you can use as a residue. But here, these are the shortcut ways finding out the same residue value. So you can still use the Lorentz series and find out c minus 1 value. It won't give any difference. Got it? Ranjit? So note down one problem based on this. Find the sum of the residue of f of z is equal to sin z by z cos z at its poles inside the circle. Z is mod z is equal to sin z divided by z cos z at its poles within mod z equal to 2. So can you find the residue of it? Anybody got the answer? No, it's not correct. At one pole it is 2 by pi. That's correct. But total there are 3 different poles are there. Anybody got the answer? So at one pole it is 0, another pole it is at 2 by pi, and there is one more pole. See this, let me find out. So here the region of integration is mod z is equal to 2. So this is the circle of radius 2. So this is mod z is equal to 2 is the circle. Now within this circle there are different poles. See this, the poles are nothing but which makes the denominator 0. So there is one pole, simple pole z is equal to 0. This is one pole. And another place is cos z is equal to 0. When cos z is equal to 0, the possibilities are, one is pi by 2 plus or minus, and plus or minus 3 pi by 2. And these are the places, and plus or minus 5 pi by 2. So these are the places where there is a pole possibility that can occur. Now here, this plus pi by 2 is coming out to be here, minus pi by 2 is coming out to be here. But 3 pi by 2 and more will be outside the region of integration. Then we don't need to consider, because Cauchy's theorem states that if this is outside, the singularity is outside the region, then there is no need to consider those poles. Now here there are three different poles. This is one pole, and this is one pole, and this is one pole. Now we take the first pole, that is z is equal to 0. So residue at f of 0 is nothing but limit z tends to 0, z into sin z by cos z into z. So this z will cancel out. Sin 0 by cos 0 is nothing but 0. So this is one residue. And another residue at f of plus pi by 2. Now this is limit z tends to pi by 2, then z minus pi by 2 into sin z divided by z cos z. Z cos z. Now this is the place. Now here, when z is equal to pi by 2, this will become 0. Now this is the second case, what we have discussed in the previous. So this is, the cos z is coming out to be 0. Now we can make use of the L'Hospital rule. Now you take the numerator and the denominator. So z pi by 2 and derivative of the denominator. So you can substitute it. Got it? So apply L'Hospital rule on this, and then directly you can find the value. So z minus pi by 2 into derivative of sin z is cos z plus sin z into derivative of z minus pi by 2 is 1, and then in the denominator z into derivative of cos z is minus sin z plus cos z into derivative of that is 1. So this is limit z tends to pi by 2. Now if z tends to pi by 2, this will be 0 and this will be 1 and this will be minus pi by 2 into 1 and this is 0. So this is 1 by minus pi by 2, this is minus 2 by pi is one residue value. By pi, not pi by 2, I think. Got it? Exactly in the similar manner, if you do the z tends to minus pi by 2, then the residue value will be coming out to be 2 by pi. That is at other pole, at this pole, minus pi by 2. Now the sum of the residues, sum of all the residues, this is 0 plus 2 by pi minus 2 by pi, this is coming out to be 0. Clear? Any questions on this? Limit part, what you don't understand. So here it is a 0 by 0 format. You have applied L'Hospital rule. Numerator separate derivative, denominator separate derivative, and substituted the value. Nothing more than that. Understood, Liju? So note down one more. Determine poles of the function. Poles of the function z square by z minus 1 whole square into z plus 2. And the residue at each pole, hence evaluate. Hence evaluate integral f of z dz, where c is the circle mod z is equal to 2.5. So can you solve this? I'll give you 5 minutes time. You try to solve on your own. Anybody got the answer? Yeah. So I think so 4 by 9 and 5 by 9 are correct. So these are simple cases only. So this is a simple pole. So you can find out residue at f of minus 2 is nothing but limit z tends to minus 2, z plus 2 into z square divided by z minus 1 whole square into z plus 2. So these two will cancel out and z tends to minus 2. This is 4 divided by 9. Similarly, residue at f of 1. Here limit z tends to 1 and d by dz of, so only one derivative because n minus 1 is 1. So 1 by 1 factorial into d by dz of z square into z minus 1 whole square into z plus 2 into z minus 1 whole square. This z minus 1 whole square and this z minus 1 whole square will cancel out. And then take the derivative z square by z plus 2 and substitute z is equal to 1. You will end with 5 by 9. So these are the residues. Then as per residue theorem, integral over the closed contour C f of z dz equal to 2 pi I times of sum of the residue 4 by 9 plus 5 by 9. So this is 9 by 9. The answer is 2 pi I. Got it? Understood? So this is one such integral. Evaluate, next one, evaluate integral over the contour C tangent dz. Tangent dz, where C is the circle, mod z is equal to 2. Can somebody solve this? Anybody got the answer for this? Yeah, that's correct. Minus 4 pi I. So this comes under the case 2. So this can be written as integral over the contour C sin z by cos z dz. Now here mod z is equal to 2 is the circle. So this is of radius 2. This is the radius of 2. In such case, cos z will be 0 at z is equal to plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Now, as pi by 2 lies within the circle, this is plus pi by 2 and this is minus pi by 2. So, these are the two values. So, where this will become to be 0. Now, here if this is the case, then sin z by cos z, limit z tends to pi by 2, sin z by cos z. So here I have explained earlier. So how we will be finding out the residue values. Now here it is not 0 by 0 format, but denominator is coming out to be 0. In such case, sin z divided by derivative of cos z, limit z tends to pi by 2, where one pole is there. Now derivative of cos z is minus sin z. This will come out to be minus 1. So sin z will cancel out and this will be minus 1. Limit z tends to minus pi by 2, then sin z divided by cos z. So d by dz of cos z. So this is again coming out to be minus 1 only. So the sum of these residues 2 pi I times multiplied by minus 1, this is minus 4 pi I is the integral value. Clear? Any questions on this? Any questions on this? So this is about the residue theorem. So there is only one class that will be left over after this, that is contour integration. So other than that, rest of the things are covered. So this is one of the simplest topic and easy syllabus, very less syllabus. Got it? So contour integral will be one class. So that's all for today. Not Laplace equation, Laplace transforms. So Laplace transforms, so I am going to cover it. I think so. Such as are left it, right? I am going to cover Laplace transforms. Don't worry about it. Got it? So yeah. So that's all for today. Thank you.